So in this video we're going to continue with our discussion of stoichiometric coefficients. If you remember in the last video we talked about the so-called simple case, and it was simple because if you have a system like this, reactant A only appears on the reactant side, does not also appear on the product side, and likewise B in this case only appears on the product side and does not appear on the reactant side. In this situation it was fairly straightforward to write down by inspection the stoichiometric coefficients. All reactant species are negative, followed by the stoichiometric amount, which in this case is 1, and all stoichiometric coefficients for the product were positive, again followed by the stoichiometric amount. So the case we want to consider in this video is a situation such as this. So in this case the reactant A actually occurs both on the product and the reactant side. Right? In this case we have to do something slightly differently. I'm going to indicate the stoichiometric amounts using these symbols. I'm going to use alpha A to indicate the stoichiometric amount for the reactant side of A, which is 2, and I'm going to use pi to indicate the stoichiometric amounts on the product side. In this case A is 1, in this case B is also 1. Now the stoichiometric coefficients, fairly straightforward to compute, so I'll write them down here. Again there's 2, and there's 2 because there's 2 species. B only appears on one side, so it's actually we use the same rule as before, so that's plus 1 because it's a product and followed by 1 because its stoichiometric amount is 1. Now for A, however, we have to take the difference between stoichiometric amount on the product side minus the stoichiometric amount on the reactant side. So that gives us minus 1. So at first glance you may think that the stoichiometric coefficient of A would have been minus 2, but it isn't. And maybe on second thoughts it might have been plus 1, but it isn't either. It's in fact minus 1. So to show you a more complicated example, let's consider this one. So 2A, say, plus 3B reacts to form 3A plus, let's say, 2B plus C. So I'll label all the stoichiometric amounts. So alpha A is 2, alpha B is 3. Remember now we've got 2 reactants, so there's 2 alphas. We got pi A, which is 3. We have a pi B, which is 2. And we have an additional one, pi C equals 1. Now again, as before, there are 3 species, so there are 3 stoichiometric coefficients, which are labeled Ca, Cb, and Cc. And to compute these, we take the difference between the product stoichiometric amount for A and the reactant stoichiometric amount for A, and likewise for the others. And now notice I didn't write down the alpha C, which I should have, so let me put that up here. So there's no C on this side, so we can say that alpha C is 0. Okay, and we can actually compute these numbers as follows. So pi A is 3, 3 minus alpha A is 2, which is 2, leaves 1. Pi B is 2, 2 minus 3 minus 1. And finally for C, 1 minus 0 is 1. Right, the C actually we could have estimated the C one just from the normal rules. So these are the stoichiometric coefficients now for the different species. Now you may wonder why go to all this effort. Well, by formalizing it this way we can encode this in computer software. So if a computer program were given this reaction, it could compute the stoichiometric coefficients for us. This has become very important when we then come to write down the rates of change for more complex systems.